Tonight's session is about Snowflake, and from somebody who works for Snowflake, 4 things that they like about it is going to be quite an intriguing approach, I think. Ron Dunn, who I've known since he was actually in Microsoft days and moved across. So definitely a long-standing knowledge around analytics and systems to run them, and hopefully he's going to have a display screen to be able to present to you this evening and see what's on.
It comes back. It kind of comes in and out.
Okay, so we can go to one thing we don't like about this meeting room. It's very easy on the screen. But I will pass on to Ron to give his own introduction of himself and the session time.
Let's just make sure this works. Yes. Okay, great. Thanks everybody for coming out tonight. I'm a sales engineer with Snowflake, and I did that job for a long time with Microsoft prior. It's an interesting space to be in. And what I'm going to try and do tonight is to talk about Snowflake pretty much from the perspective of a SQL Server person. So I'm going to talk about the things that I like about it in comparison with the SQL Server world. And I'm going to talk about the things that I personally found difficult in going from a SQL-centered world to a Snowflake-centric world, and some of the things there. Now, anytime you've got questions, just jump in and ask it. There'll be plenty of time at the end of the session for questions, but I don't mind questions as we go along either. It's going to be a slide light night. I've got 4 topics that I want to talk about. I've got 2 slides for each one, and I've got 3 demonstrations that I want to do. So I think you can tell from that there's going to be a lot more lines of code and demonstration than there is actually slideware. So there's plenty of opportunity to jump in and ask questions as we go. Okay, so let's talk about the world of Snowflake. First of all, we're going to talk a little bit about the architecture. Now, there's no demo associated with this, but there's a couple of points about Snowflake's design and architecture that I really want to call out. This is the only marketing slide that you're going to see, and this is because Snowflake refers to ourselves as the data cloud. Now, we're a little bit more than that these days because we're not just about data, we're about applications and logic as well. I'm not going to put too much time into talking about that today because we're all data people. I'm going to focus on the data aspects of the platform. But really, Snowflake's mission is to provide one global infrastructure for people to store and collaborate using data. And that's a pretty powerful type of mission. Let me drill into that just a little bit more. This is how we view the data cloud. This is a graph that we drew about a year ago, which was major sharing paths for data within Snowflake. Now, I'm going to talk about what sharing is and how we actually implement it in just a moment. But what this is showing you is some of the loci of sharing within the Snowflake market. We have a number of organizations who provide data, which is consumed by a great many organizations across the world. And what's unique about Snowflake is going to come up in the next slide when I talk about what the layer of platform architecture is. But when we share data, it's not about moving data from one place to another. It's not a share through FTP or through storage or anything like that. It's a live, queryable component of your database. So if I construct a share with Guru, for example, Guru can refer to a table in his query on his database as Ron's share.schema.table name, and it will perform exactly the same as if he'd copied that table into his database. That's what's so special about our sharing. The table acts as if it was created by you in your database. There's no copying, there's no movement of data unless you unless you decide that you actually want to do that. Now, I said I'd drill into the architecture. This is a block mode diagram. Let me talk through the various components of it. The key message, and perhaps the biggest differentiator of Snowflake compared to any of our competitor products in the marketplace, is that we have exactly the same product running on 3 major clouds. So we're on Google, AWS, and of course, Microsoft. I spend most of my time with Microsoft customers, but the only way that I really know that I'm running on Azure as distinct from AWS, for example, is the format of the URL that I use to connect to storage, or the format of the credentials integration, for example, that I use to work with, what's the new name for Active Directory? Thanks. I knew it had a new name, but I couldn't remember what it was. So it's only where we actually connect to a specific service on the host that's not a generic interface that we become platform specific at that point. Everything that you'll see me do tonight, I'm going to do on Azure, but I could have equally done with exactly the same lines of code on any of the other platforms that we support. That's special, number one. The other thing that's special is this thing here, this one in the middle, called centralized storage. Now, for those of you who are used to Microsoft and a SQL Server-centric world, your data is stored in MDF files or LDFs, depending on how it's arranged, and there's possibly pointers to clustered column store indexes as well. But basically, the data is stored within one encapsulation, and that represents your database. That database is stored in a location that is specific to you. Snowflake does it differently. Every customer's data in a particular region is stored in our storage. The database, the table, the schema are logical abstractions over the data. All of the data is stored in the one location. And this is how we get that sharing advantage that I spoke about earlier, because it's not like we have to pick up a table from one MDF and move it to another MDF before you can reference it or put it on storage with an external table link. We are sharing that table as it exists in our storage. And that sharing is governed by the permissions that you put around it. So we have boundaries around things like account, around tenancies, around databases, around warehouses, which are our compute clusters, etc. But you define how they get granted to people within your organization or people within other organizations. And this is where the magic of Snowflake sharing happens, because there is no data movement unless you want to share across clouds or across regions. If you want to share with someone in the US, for example, for performance reasons, you might set a US-based region and a replica of your shared tables to that region so that they get super fast responsiveness in that region. The same if you wanted to share across cloud. We don't put boundaries on our customers that say you have to be on Google, for example, to share with a Google customer. Now, we will have to replicate to Google in order to do that, but once you've done it, that data is available for any customer in that region, should you choose to share with it that way. So this is pretty much the core of the magic that happens within Snowflake. The other part of the magic in storage is the way that we store the data. When we store the data for a table, we do it in something called a micro-partition. And a micro-partition is a little bit like a Parquet file or a little bit like a clustered column store index file, which stores around 10 to 100 megabytes of data. And as we bring data into a table, we fill up these micro-partitions, one after the other or in parallel, depending on the type of the operation, and we catalog them in a metadata catalog. That metadata is incredibly important because that tells us what files comprise a table, and that's how we build up our sharing, our relationships, our security, our RBAC, all of those types of things are driven from that. And these micro-partitions are at the heart of our time travel and our cloning architecture, because micro-partitions are immutable. Every time we change a row, we rewrite the micro-partition, and that's how we can go back through generations of a table back in time, etc., as you're going to see me doing in a demonstration in a little while. The other part of the architecture that is somewhat unique is this multi-cluster compute that you can see just here. Snowflake has absolute separation between compute and data. There is no relationship between those micro-partitions and a given compute engine, and there is no one-to-many relationship. So it's not like you have a warehouse that comprises a number of tables. Now, I said I'd do two things that I don't like about Snowflake. I'll add a third one that's a little bit of a conceptual shift that you have to do if you're coming from, say, SQL Server to Snowflake. We use the term warehouse to mean compute engine. So when you hear someone talk about spinning up a warehouse, that means spinning up a compute cluster. And that's going to use the data that's in your centralized storage and your micro partitions. And it'll be dynamically assigned at runtime, depending on what your queries look like. So when we talk about warehouse, it's not the database, it's the compute engine. We have no relationship between databases and compute engines. I can have 5 different compute engines all working on the same set at the same data set at the same time. I can have one compute engine accessing information from multiple databases, accounts, and shares on exactly the same queries at the same time. And this is where we get amazing scalability, both in terms of concurrency and power. And I'll talk about that when we go to demonstration in a moment. So they're probably the biggest architectural differences between a SQL Server environment and a Snowflake environment. Now I want to drill into a couple of the things.
Question, Ron?
Yeah, absolutely.
So just on that description with warehouses and the compute, is it per user? So would different users get potentially different compute, or would users share the same warehouse?
Yeah, it's both, and that depends on how you set it up. But usually you have multiple users connecting to a warehouse. Now, users might be a set of ETL jobs, a user might be Power BI, for example, or users might be individuals who have got a connection string that connects to a compute engine. But when you connect to Snowflake, you specify the compute engine that you're connecting to, and you specify the initial database that you're connecting to. And you'll see me modifying those when I go through demo in a moment. Okay, so the first thing that I want to talk about
is a couple of questions, just really briefly, so I don't lose track. With the micro-partitioning architecture and the abstraction that you're talking about, does it work with both OLAP and OLTP scenarios? And does it support foreign keys?
Okay, now there's a couple of things to unpack in that.
Yeah.
The first one is, does it work with OLAP and OLTP? Snowflake, as it stands today, is primarily an OLAP implementation. There is a feature that is coming, it's been announced, and it's in private preview at the moment, which is called Unistore or hybrid tables, depending on which bit of documentation you read. That is designed to support OLTP workloads on Snowflake. So we're branching out from being a pure analytics engine to being a transactional engine as well. Will it support hundreds of thousands of concurrent users? Would it replace your SAP database, for example? No, it's not designed for that workload, not for the next few years at any rate. But it is designed for the things that you might use a departmental type SQL Server for that level of transactional integration. The next thing that you asked about was foreign keys. We support the definition of foreign keys, and they're used by the optimizer to optimize queries. And they can make quite a significant difference to query performance if we know that we can rely on a foreign key definition. But the maintenance of foreign keys is up to you as the developer. And that's the same on every one of the MPP architectures.
Yeah.
And the reason for that is because on an MPP, massively parallel processing platform, you have a number of different computers that are acting on the data at the same time. And if I had to say to every one of them, do you know about this record, or can you go and delete these dependent rows in this foreign key relationship, your performance would fall in a heap. So all of the MPP engines take the approach of saying either we don't support primary and foreign keys at all, or we support them as an optimizer hint rather than an enforced constraint within the database.
Thanks.
Hey, Ron, it's Greg.
Yep.
Listen, just one quick question on that. What I've always wished the MPP engines had is a switch where you could turn it on and off. Because if I'm testing something, I want it to tell me that I've got the transformations and stuff wrong. But I want to be able to turn it off once it's in production.
Interesting. I'll take that one offline with you, Greg, because that's a really interesting idea. I'll get some more details and we'll put that one into the suggestion box, I think. Okay, back to compute and performance. One of the things that Snowflake does exceptionally well is concurrency and scale, and I'm going to show you an example of that shortly. The reason that we handle this so well is because we can run multiple compute engines on the same set of data at the same time. So what this means is that if you have a collection of data, let's call it a database, which is your order processing database, and you want to run an ETL workload against that, as well as a reporting workload. If you're using a SQL Server or a Synapse or something like that, you now have a bit of a problem because they must act within the one compute engine on that one database. And that means that often your ETL queries can be in conflict with your user queries. They're blocking or they're taking up resources, and one workload isn't getting sufficient resources compared to the other. Snowflake breaks this by saying you can spin up one compute cluster, which is doing your ETL, and it can get 100% of its resources, and you can spin up another 5 clusters, which are doing power.
No.
At various points through the flow, depending on what you're doing with those ETL queries, but you'll never find a resource contention from the point of view of memory or CPU, because you can spin up as many clusters as you like. When we talk about concurrency, Snowflake can spin up to 10 instances in a cluster, each of, we've lost our screen again. I'm told it'll come back. Each of them is of different scale. So this is what we call a scale out. And each instance, we typically recommend as running around 8 queries. So a given scale out cluster, we recommend to handle somewhere around about 80 to 100 queries. But because we can have multiple clusters, each doing the same job, then your concurrency is virtually unlimited, depending on what you're prepared to pay in that case, because you can run as many clusters as you want in parallel on the same set of data. So scaling out is about concurrency. Scaling up is about performance. So when we talk about what we call t-shirt sizes, small, medium, large, extra large, that's about adding more cores and more memory to the query and more I/O, depending on the number of worker threads that we might need for a query. So we scale up to get the resources that we need to run the queries. We scale out to add more of those queries at the same time. So we don't have that cap and we don't have that resource group contention that you get in some other platforms where they're fighting for the same set of resources within the same query engine at the same time. So Snowflake is a pretty
One
good
question
scale.
on that.
Yes.
Sorry. So let's say we had hundreds and hundreds of end users all doing their reporting queries.
Mm-hmm.
Wouldn't that mean that we need quite a few logical warehouses for them to connect to?
Yes and
to get
no.
this concurrency?
Yes and no. It depends on a couple of factors. The first factor is, are they all hitting exactly the same queries at the same time? Probably not. A typical industry ratio is something like 10 to 1 for the number of concurrent. In a heavy BI scenario, It's roughly 10-to-1 ratio between the number of concurrent queries versus the number of users. The second part to that answer is what's the duration of the queries? Because if you can cut down the query duration, then you can pack more into a given 10-second window, for example, or 3-second window, depending on what your user feedback requirement is. And the third part of the story is what we call result set caching, which is where, and a number of platforms have this, which is where if you're executing the same query, it will retrieve the results that have already been generated rather than going and re-executing that query. So there's no load in order to do that. And that handles the typical slicer plus fact table type problem that you might see with Power BI. Now, there's a whole lot of best practices that go around what you do with Power BI for a Snowflake or a Synapse or a Redshift. And all of those apply equally across those platforms. But we can certainly handle a lot more concurrency if you're prepared to pay for it.
Right. So you're saying before that you scale up for performance and you scale out for concurrency.
Correct.
So we've done all those good things about tuning and making it fast and caching, but we still need to scale out for more concurrency.
Yep.
Does that mean that each group on that will have a different connection string to get to their own virtual warehouse?
No, it's the same connection string in a scale-out cluster.
Okay, cool.
We handle that automatically. And the other great bit, I wasn't going to mention this, but since you brought it up, I will. Snowflake has the ability to dynamically scale in and out. So if you set up a cluster as having a maximum of 10 instances, we will only fire up those additional instances as there's submission demand. And when the demand drops off, we'll automatically shut them down, and we'll automatically shut the whole cluster down when there are no queries happening on it. So that we do a lot to try and optimize for where the spend happens within Snowflake. This graph talks about one of the major benefits of a platform like Snowflake, and that's the relationship between scale and time. Now, what's saying here is that if we needed to load 1 billion records, if we could do it on an extra small warehouse, and that's only got 8 reader threads associated with it, so it takes a chunk of time. If we scale up to a small warehouse, that doubles the number of cores and readers, and so it roughly halves the time, because we can apply more readers to the files that are on the disk, and we can ingest more data in parallel. And the same when we scale up again. We double the number of cores again, double the number of workers, and that means that, again, we can roughly halve it. Now, Snowflake pricing operates on the same linearity, that as you go from extra small to small, you pay twice as much, but your workload takes approximately half the time. So you get a roughly neutral up to somewhere between a large and X large relationship between time and cost for a given workload. Why wouldn't you run all of your workloads at extra large all the time? Well, not all of your workloads benefit from extreme parallelism. Ingestion is one that does, whereas some queries, if they're aggregation heavy, for example, don't benefit to the same extent. So transformation doesn't necessarily benefit as much. The second one is that while Snowflake can shut down automatically, you can configure the time that the system is quiet before it shuts down, anything from 1 minute up to hours. But every time it shuts down, it evicts the cache. So if you're in a high performance environment where you want to query cache of your hot data, if you've paused your cluster, you've lost that cache, and there's a time for which your queries will run slower while that gets rebuilt. So you don't want to be running large clusters all the time. Otherwise, your bill is going to be a little bit higher than you want it to be. So there's a trade-off on how slow are you prepared to accept a query in order to trade off some of the costs that are associated with that. The other really good thing that you'll see me do in a moment is that scaling up and down is instant, and it can be done in the query text. So I can be running extra small, extra small, extra small. This next step's really big. Let me scale right up. Scale up, done. run that query, scale down again in the script that's associated with it. So there's a lot of control available to you. Here's a real world one that I did recently where I was ingesting 100 million rows in this particular case, and I was using one of two methods to do it, a copy into statement and an insert statement. And that's the demo that I'm going to do in just a moment. And you can see at different scales, we roughly halved the time that it took to ingest those. And you'll see in a moment just how quickly we can ingest that piece of data. So let's go and look at a demonstration. And here's my Snowflake. Okay, so this is a user interface called Snowsight. This is our user interface. This is one of the things that I don't really like about Snowflake. One of the things that I think Microsoft does better is that Microsoft has 40 to 50 years of IDE development under its belt. And coding tools are something that Microsoft does particularly well. Our guys are database people, and sometimes some of the usability decisions that they make around Snowsight, which is this user interface, are a bit on the funny side. So I would rather develop in VS Code, for example, which I can do, but I don't necessarily get all of the facilities that are available here that I want to use for a demo. So look, it's okay, it works, but some of the things that you need to do. In Snowflake, you need to say which database am I going to use. That can be done at connection time, or it can be a default for a user, or I can do it here. I'm going to use this database called BFT, and that's now run. You can see down here that that's executed successfully. I'm going to pick a compute engine. I can have multiple compute engines that I'm using, and I'm going to use this one called BFT. Here's the other bit of bizarreness. The way that RBAC works, you need to pick your role. It's not like you sign in and with AD, you have a group assigned to you and you get all of your privileges from that group. In Snowflake, you have a wide variety of roles that can be available to you, and you have a concept of primary and secondary roles, which are like the combinations of roles that might be there, and you need to know which one you want to use. So when you're coming from a SQL Server world where you're used to it being dictated by your AD group and everything's assigned by a DBA from there, this one can be a little bit disconcerting at first, but once you get used to it, it's okay. So that's what we call setting the context. I've picked a database, a warehouse, and a role, and I could also pick default schema and things like that if I wanted to, but I don't need to. Now I'm going to step over the next little bit of code because that's just creating some data, and I've already done that before this session. One of the things I really like is that Snowflake can work with your storage from within Snowflake. So have you ever had the problem where someone's put some files in a data lake and you want to know what's there, and you have to go out and you have to load Azure Data Explorer, for example, to go and look at the Storage Explorer, to go and look at ADLS, find the container, find the files, look at it there. And if you want to add up what the volume of those files is, you can't, because that's not part of the feature of that particular tool. Snowflake does a reasonable job of addressing this, and it'll show me some of the features of Snowflake that make that useful. So, for example, if I run this one, ls Azure, I've defined a storage integration called @Azure, which is just pointing to one of my containers on ADLS, and I'm looking at a folder within that called BFT, and it's listed the files that are in that folder. But I can do sums over this or calculations over this, for example. So if I come here and I run this particular query, it tells me that that folder contains 1,300 odd files and 26 gigabytes of data. Now, something I like about Snowflake, see this results scan last query ID. That takes the results of that particular query and surfaces them as a table. So I've done that query, I've got the results, which was all of those files that you saw before, and I can interrogate that and write queries on top of that if I want to. And it becomes incredibly powerful for being able to operate at the file system level. So we can see that we've got all of those files. What I'm going to do here is scale up because at the moment I'm running at an extra small configuration. So I'm going to scale that up, and now that's already executed successfully. And you'll note that I said wait for completion equals true. I'm now running at a very high scale configuration. I'm running at an extra large. It is expensive to run at that, but it's not like the 15 minutes to 30 minutes that you get as a scale time on some other platforms. So in this case, what we're going to do is to interrogate some Parquet files. So I'm going to start off with a file format, which I've already done. Now, when we have files in our folder, we can infer schemas from those. So rather than having to go and get the schema for Parquet defined in advance, then I can just run a query like this, which says, go to that location, read those files, and generate a schema. So there's the schema that it's pulled out of all of those Parquet files that was there. So it's looked at each of the Parquet files, said, here are the columns, here's the nesting, here are the array definitions, and pulled that out as data in this particular case. But we can get a lot more clever with it than that, because I can take that schema that I've used there. So you can see here that I'm inferring the schema, and I can create an array aggregate of that, which says take out the columns and aggregate them. And I'm going to create a table using that inferred schema in my database. So when I run that, it'll take about the same time to execute again, about 6 seconds, I think.
That internal bit there on the from table and infer schema.
Yep.
Could you have used again the last query?
I could have. You can do any of that at any time. So if I look at the schema of that table now, you can see, let me just pull this one over here. There's the table definition that is created. So it's created a table that is going to match the schema of all of those Parquet files. And now if I want to ingest some data, we're going to create an external table definition, which is creating a logical mapping over those Parquet files. And I'm going to use exactly the same technique to do that. So I've now defined that as an external table. And the fastest way to ingest the data is using an insert into statement. And I'm going to dynamically generate that by using exactly the same sort of technique. So if I do this, it will dynamically generate my insert into statement. So if I look here, you can see that it's dynamically generated the code that I want to run to ingest the file. And if I want to run that, I've already pasted it in here. I'm going to run this now. So we're going to ingest 26 gigabytes of data from those 1,300 files. We'll see how long that takes.
And that's in block storage, Parquet.
Yeah, this is in ADLS at the moment.
But you're ingesting it into a table in your internal storage.
Yeah, this is coming into internal storage at the moment.
When you do that, do you have any controls around how that's stored, like in the context of like Synapse dedicated SQL pool where you have round robin?
No, you don't need that. One of the differences between Snowflake and Synapse is that you don't care about distributions. The micro-partitions, because we keep all of that metadata about micro-partitions, and for every column in a micro-partition, we know its minimum, maximum, whether or not it has null values, etc. We dynamically assign those to nodes, so there's no distribution that's required and no round robining, because we can take the same file and point it across all of the nodes if we want at any given point in time. So it's an optimizer problem rather than a design time problem.
Do you use indexes?
Nope.
So it's
hang on. Now, let me go back on that. Do we use indexes? In general, the answer is no, but there's a feature called Search Optimization Service, which uses Bloom filter indexes to dynamically reject large numbers of partitions during a query.
to dynamically
Reject. When we're talking about what we read from a table, look at the metadata catalog and say, which micro partitions do I need to worry about based on this query, based on whether rows are in there that satisfy the query. The way to increase performance is to look at fewer partitions because that's what we need to read from disk. And the way we do that is by trying to prune or reject as many partitions as we can. And a search optimization index helps us to do that.
Can I just say, oh, sorry.
No, go and finish off yours.
It's interesting in the Synapse dedicated SQL pool world where it handles, it's amazingly performant when you're handling in a query a large volume of data. As soon as you shift, I mean, obviously it's massive parallel processing architecture isn't really designed for it. But when you shift to more like row by row processing, the whole performance of the architecture just grinds to a slow pace. So with Snowflake, how would that compare? Would it be similar?
Similar.
Or does
Similar.
it have additional smarts that...
Well, under the current architecture, remember I said we had that uni store that was coming. Under the current architecture, it would be roughly the same because if you're doing row by row processing, then we need to retrieve those rows to a specific node to do that. And that's where the slowness is on both platforms.
Yeah.
Our Unistore will make that a little bit different. So you can see there that this query took 26 seconds to do that ingestion. That 26 gigabytes of data is 100 million rows. Think about your business. Most of your businesses don't do 100 million events in a day. Some of you do. If you're working with AMO, for example, the number of meter readings that happen is greater than that. But if you're working with a supermarket or a retailer or someone like that, you're not doing 100 million events in a day. You've just ingested your day's data in 26 seconds. So that's one of the reasons that we like Snowflake from an ingestion perspective.
The insert stuff, Ron, so you started off there, the source stuff was in ADLS.
Yep, ADLS Parquet files.
And this is now into Snowflake's own storage. So you
Correct.
actually moved it out of Azure into your storage.
Correct.
Yep.
Yep. Okay, so let's go back to the presentation and pick up on the next topic that I wanted to talk about.
Do you have different types of storage?
No.
Is it all uniform?
No, it's uniform storage,
Yep.
but there is something coming down the pipeline for tiered storage for customers who have got very large volumes of data.
Mm-hmm.
However, one of the industry trends at the moment is towards what we call file formats rather than database native storage. And by that, you've probably all heard about Delta versus Iceberg as file formats. I think that the use of file formats and external storage is going to overtake the tiered storage that we might have provided otherwise within the DBMS. My personal view is that in DBMS is always going to be better performance, although the guys that are working on our Iceberg tell me that I'm wrong, and I'll be really happy to be proven wrong. We'll wait and see. So, yeah.
Just on the file formats, do you get a choice of choosing the file format when you import? I suppose by default.
No, at the moment, when I did that ingestion then, that went into Snowflake's native format. We're in private preview at the moment on our Iceberg format. In fact, in the second round of private preview, we had one a little earlier this year. We're doing a second round of that now. And there you'll choose between what we call managed Iceberg or external Iceberg, and that really says who's responsible for maintaining the catalog. But at the moment, if you want to integrate, you can integrate with external Iceberg or external Delta. How that translates into the future, I better hold off until I go through the preview.
Because and is Iceberg very similar to, let's say, the Delta? As in, it's a Parquet file, it's a metadata on top.
Yep, very similar. The difference is the organizations that control it and the degree of open source that's behind it. But basically similar concepts.
And in terms of performance, if you were to ingest in an Iceberg with the same thing, have you noticed any difference in both?
Yeah, at the moment.
Or do you recommend to the clients one versus the other?
Right now, my recommendation is to go with the internal Snowflake tables. And the reason that I say this, There'll be architects who'll say that we want to use external storage and we want a storage independent or a vendor independent table format, etc. Those architects are not the people who get called at 3 a.m. because the batch is running too slowly. I've never had anyone say to me, make these queries slower, but put my storage here, for example. It's always been about performance optimization, and at the moment, internal tables are faster. Like I said, devs tell me that's going to change. Okay, the next thing that I wanted to talk about was around cloning and time travel. Now, this is enabled by the micro-partition architecture because those micro-partitions are immutable. Every time we change data, it's a new copy of that data, and we keep a history of those old copies. That's configurable from 0 days, which means I'm keeping no history, back to 30 days, I think. Yeah, I forget the number. Anyway, irrelevant. So I can decide how many generations of data I want. That comes at a cost because you're paying for the storage associated with it. But on very volatile tables, you can end up with a lot of storage over that time. Storage is cheap, $25 a terabyte a month, somewhere around about there. But it's still a cost that you're paying if you're churning very, very big tables all the time. So the way that it happens is that we take a copy of those micro partitions and hold that in our metadata with timestamps. So if you say that you want a copy of a table at a given point in time, then all you need to do is to specify the timestamp at which you want that data. So let me go and show you an example of how we actually do this. I'll go back to the query here. And we'll come to this one. Okay, so I've got a slightly different scenario that I'm going to run through now. And in this scenario, I've been doing some development work and I've got some problems in my development. There's been an error reported that one of the columns in my database is wrong, and I need to add a new column to my database. So typical developer type jobs. And this is where something like zero copy clones, which is a metadata repointing, so that we take a new table and say it represents this set of files that you already have. And when we modify that, it creates new sets of files. And we're going to use time travel to fix up a problem that I'm going to make. So here I'm going to switch that role that I talked about when I spoke about having context. And in this case, what I'm going to do is I'm going to clone a table for dev test. So I'm going to create a table as a clone of a table that's already there at the moment. So I'm going to take my truck table and I'm going to call it truck dev. So if I do that, I've now cloned that table. The clone is not a physical copy. So I could take a 100 billion row table that takes up a petabyte on disk and say clone it, and it will happen in almost exactly the same time. Now, where it's different, why it'd take a bit longer rather than being not instant, is that you would have far more metadata files, and copying the metadata pointers would take a bit more time. But it's not as if it's going to take me hours to copy that, as you have to do with a backup and restore or a CTAS type operation to take a copy of a table. So we've done that. What I'm going to do now is assign some compute. So I'm going to say that I'm going to use this tasty dev WH, and I'm going to look at the data that's in that table, and you'll see an example of the problem that I've got. You can see here that for some reason I've got an underscore on the end of the word forward. There's been a problem in my data loading. I need to get rid of that, and I need to add a new column to this table, which is going to represent the age of the truck. So I'm going to update that. So I'm going to set the make equals forward. So I'm going to do that particular update. We've updated 160 rows. That's good. We've corrected that. And now I'm going to add a new column, which represents the age of the truck. So we'll just make sure that we've got something there that looks right. We've got some data here. Yep, okay, I've got some ages there. That's good. So I'm going to alter that table, add that column, which we can do quite simply. This is just standard SQL at this point, and I'm going to calculate the truck age and update it. So we've done that. But if I go and validate that, so let's pick this up again. We'll pick up the truck ID and the age. All of the ages are 1. So I've obviously done something wrong. I've written my query incorrectly. And what I've done wrong in this case is that I've got this calculation wrong. I've said that it's the current date, the year of the current date divided by the year, which is wrong. That's obviously always going to be 1. So that's where I've gone wrong. Let's recover that particular table. So here, I can query all of the metadata through a metadata table called query history and say who changed this table and when. So if I run that, we can look at that and we can see a bunch of changes that have occurred to that table. So you can see that I've got a couple of updates that have occurred to that table. Okay, so it could be either of those that represent the query that was in error. So what I'm going to do is find a different one. So I'm going to look for the queries where we did an update, but we set the track age so that I'm not getting this make equals 4 that I'm setting down here. So I can pick that individual query out. You can see that I've set a query ID. Okay, so if we select that query ID, we can see that the query ID within Snowflake has a GUID associated with it, which you can see there. And because we keep all of this metadata, I can say to roll that table back to the point immediately before that query ran. That's because we've got all of those micro partitions and all of those dates. So if I run this, I've now rolled that table back to that point. Now we can go and look at applying that calculation correctly. So it should be minus the year rather than divided by.
Just quickly.
Yep.
At this point, can you roll it forward again?
Yes, I could.
Yeah, okay.
Yep. And let's take a look at the data this time. Did we get that right? Yep, we've now got some ages in that last column that look correct. So now let's roll those changes back to production. So I'm going to say that I'm a sysadmin. I'm going to swap those two tables and I'm going to delete the table. There. Okay, what did I do wrong there? All right, this is pretty silly. This is a contrived scenario. But what I've done wrong in this case is I've deleted the table when I shouldn't have, and I can, of course, undrop it. So now we have that table back. You can drop and undrop tables, databases, schemas, any of the standard objects. So if you, I remember one time very early in my career, I dropped a database after a liquid lunch. That took a bit of recovery, both in career terms as well as in technical terms. But with Snowflake, that's a nice little protection that you can undrop any object at any time. And now if we look at that, we'll see that we've got our validation correct. And I've done something wrong there in the middle of talking. Don't worry about it. That all works now correctly, so that we've got all of our data dropped, undropped. We've got our time travel. You've seen that working. So that's the way that that works. This is a really great feature.
Was it your swap that was?
Yes, it was. It was the swap that I got the wrong way around. Sorry, I think someone spoke there.
Yes, it's Michael here. The scope of time travel and rollbacks like that, is it just within your virtual data warehouse, or is it across all users of the data store? So if we made an update to our data and other people are concurrently using the database,
yes,
and we move backwards, are they going to see our undos?
Yes, they are.
Okay, yep. Right.
Because it's a table that's shared across all those users, if you roll that back, then they're going to see that as the current state.
Okay. So it's something that needs to be handled with good communication across all the user community of the team.
Yeah, normally I would hope that there's a good separation between your development activity and your production activity, so that it didn't happen that way. But I have seen it where people have needed to recover in production and use this technique in production.
Gotcha. Thank you.
Okay.
Is the separation of permission you can weakness from something? Say you don't want anyone to be able to unload.
Certainly I can assign permissions that allow me to do those things. So I could take away the permissions that support time travel.
Not legitimate. This table in particular, I don't.
Think about that. I've never had that question. I need to think about that one while I'm doing the next bit of the demo.
Like purge. Oh, I've accidentally ingested data. I shouldn't.
I need to think about that.
The storage is cheap, right?
No, but if it was the case where that data should never have made it into the system, so there was a business justification that, for example, walls of China in an organisation, the data crossed a boundary it shouldn't have, and you wanted to guarantee that you'd got rid of it, I'd be astonished if we didn't have a way to do it, but I don't know it. Yeah, I can't think of a way, but I'd be almost certain there is one. Okay, the last thing that I'll talk about for tonight that I really, really like about Snowflake is how easy it makes streaming. But there's a message that we put around streaming. And that's when people in the industry talk about streaming, they all talk about fraud detection. And they all say, in the middle of this transaction, you need to detect if it's a fraud, send the signal back immediately and stop the transaction. But how many people actually need to do that in their business? Most streaming use cases are not microsecond use cases. Let me explain that in a little bit more detail. If we think about streaming as being a continuum, so that there's the real-time event at the moment that it happened at less than a second, there's the batch process at the 6+ hours that I've got on this diagram, and we've got a way that we treat them within our organisations at the moment. The mountain of wisdom represents the reporting type or dashboard type analytics, where we're saying, how are we going compared to last year? How are we going compared to last week? Is this product selling appropriately, etc.? That's driven by our batches or our intraday batches. So it's largely a batch process. That now representing that 1 second type time frame is the fraud detection type problem. Now, the difference between what happens here is the cost of solving that fraud detection problem is incredibly expensive because of the amount of resources that you need to throw at that particular problem to handle the subsequent transaction. But the time cost of batch processing doesn't always meet the business requirement, which is that I want to see a more up-to-date focus on the data that I have, such as, is my price reduction on this particular item flowing through to my customer base in an e-commerce type scenario? And this is what we call the peak of soon after. There's a sweet spot here that says that I don't need to spend a huge amount in order to give additional value and faster data. And this is the spot that Snowflake aims at with streaming. We're not there to handle the problem that you would use a massive Exadata for example, which is if you were Visa or MasterCard doing online fraud detection, that is not what Snowflake's going to do for you. But if you wanted to do an operation within a minute to 5 minutes type duration, such as, is this product selling? Was that discount effective? Am I seeing this change in behavior, for example? These are the things that we can do quite easily with Snowflake. And the little demonstration that I'm going to close with tonight is a streaming scenario where I'm going to push some sales transactions into Kafka. I'm going to land them into Snowflake. I'm going to dynamically pull unique customers from that, so customers that I've never seen before, and populate them into a table. And I'm going to publish that back to Kafka so that that's available in a reverse ETL type scenario for other applications that might want it alongside Snowflake. in that particular case. So let's take a look at that demonstration. And out of there, the way that I'm going to do this, I have a Docker container that's running Kafka, and I have the Kafka user interface here. So I have my Kafka dashboard sitting here. I'll save that. And now we're going to go and do some Kafka configuration. So the way that I want to do this, I'm going to do a little bit of setup. So within Snowflake, I'm going to set those roles and set my context, as you've heard me speak about a few times today, making sure that I'm using an appropriate database and so on. And I'm going to set up by cleaning up any previous instances of the tables that we're going to use. So I've just dropped the tables that were in my database. Now we're going to go to good old VS Code and talk through some of the examples that's here. So we're going to use mainly Python, SQL, and Kafka to do this particular job. This first program that I'm running here simply generates transactions. It's using Faker, and it's generating a transaction ID, a customer name, a timestamp, and an amount. So really, really simple. And if I run that, okay. So if I say with a parameter of 1, it's going to generate one JSON file in this particular case, which represents one transaction. But if I say that with 100, it's going to generate 100 of them. Okay, so that's our test data. We've got our test data sitting there at the moment. So what I want to do is to configure Kafka to receive that data when I push it to it. And the way that I'm going to do that is using another Visual Studio program. Oops, wrong one. Sorry, my glasses. I'm wearing the wrong pair of glasses. Yeah, that helps me to see better. Okay, so we've got this one here called Kafka Sales Configure. And what I'm doing in this case is using the Kafka REST API. So I'm calling the REST API and I'm pushing a Kafka configuration to it to create a topic. The topic is the collection of messages that I'm going to send to it, which can then be subscribed to or delivered by Kafka to other services. So this one is Kafka Sales Configure. So I'm going to run that. Okay, so when we run that, we've got a 201 response, which is the response that I wanted. And if I go back to my Kafka user interface and look at my connectors, you can see that I've got a connector here called sales, which corresponds to the name that I put into my topic. So we've now configured Kafka. Now, this is pretty simple at this stage. It's taken us 5 minutes and we've got Kafka up and running and we've got a topic created. Now what we're going to do is send some data to that. And the way that I'm going to do that is again with a Python program, which in this case is called Kafka Sales. And what it's going to do is it's going to receive messages on standard input. So I'm going to pipe the output of that generator into this program. And for every message that I receive, I'm going to push it to Kafka. So let's do that. Kafka sales.py. Do 20,000. And we're going to send that to check that out. Okay, so when I do that, we're going to stream those records. So we've connected to Kafka. It's going there. It's sent the 20,000 rows to Kafka. But let's go back to the table that we did a little bit earlier, or go back to the Snowflake environment. So if I come back to here, and if I start to look at what's happening with that sales transaction table, that was actually, Yeah, I looked at the wrong one. So if we look here, we've already ingested the 20,000 rows. So those rows flow through automatically. When we created the topic, the Snowflake Kafka connector dynamically created the table that was associated with that as a column ID and a JSON string, and that's now stored in the database. So as soon as I push more rows in, that number will go up, and you'll see me do that in just a moment. So what we're going to do now is a new feature that's within Snowflake called dynamic tables. Traditionally, when you're writing transformations, there are two parts to the job. One is writing the transformation, which is the select or update or the CTAS or whatever the statement is that you want to do in your transformation. But the other part of the problem is scheduling. You need to have some way of running it. So you need Airflow or Control M or one of those products in order to kick the job off at a time. But how do you know in a streaming environment that new rows have come in, for example? How do you know when to trigger that new program? Well, this is why we have something called dynamic tables. Dynamic tables in Snowflake say that I can have a lag which says I'm going to do something every minute. For example, in this case, I'm going to execute that particular query and create a table that comes from it. Now, we can stack these on top of each other. So I could have the end one happening every minute and then every dependent one before that being dynamically executed as well. But I'm going to keep this simple. And what I'm going to do in this case is to create that table of customer with unique customer names that have come from my input data stream. And if I start that dynamic table and do the refresh, we now have that data. And if I look at the top 10 customers, you see that I've got a bunch of customers sitting here. So we've taken unique customers out of the stream. So what I'm going to do as my last step is I'm going to do the round robin. I'm going to go back to Kafka from Snowflake. So in this case, I'm going to come to my Visual Studio Code and I'm going to take this configuration. So I don't expect you to understand all of this. I'm not going to walk through it, but this is just a Kafka topic configuration for a data source. And in order to use this, I'm going to go to my connectors. I'm going to say create a new connector, which is going to be a JDBC data source. I'm going to paste that definition and say create the connector. Okay, so we've now created a connection to Snowflake, which is going to dynamically pull any new rows that come up in that customer table. So if we go and look at our connectors, we should see now, if I go and look at customers, already we've pulled 18,000 rows from Snowflake into there. So if I come back to here and run another 20,000 through there, we've now pushed another 20,000 rows to Snowflake, and within a minute, we should start to see all of those rows popping up in here. Now, that'll take about a minute, but we will very soon see new rows popping up in here. And that's how easy it is to do streaming within a Snowflake environment. Most of the work that I did there was related to the front-end code and the Kafka configuration. Snowflake just made it really easy to connect to those and provided the connector from Kafka to that environment. So if you're needing a streaming type scenario, it's an extremely easy product to use. So they're the four things that I really like about Snowflake and the things that my customers are getting the best value from. From an architectural perspective, the way that we handle the separation of compute and storage and the scalability of the platform is rock solid and really works. From a sharing perspective, it really works for our customers. From a scale perspective, the fact that I can ingest as many business events as any of you are likely to do in a day in the 26 seconds that you saw there is testimony to the sort of performance that we can get out of the platform. Then we looked at transformations and the way that we can do the normal sorts of transformations that people do with guardrails so that we can undrop things. We can go back in time. We can use the facilities of the DBMS to help us write code and improve the robustness of the code that we're writing. And finally, people these days have got streaming at front of mind. Businesses want to get faster with the data that they have to get that extra value. If you're looking for faster data, but not necessarily real-time data, that's a great way to do it. It works. And we've got a large number of customers doing it now. So that's everything that I wanted to talk about tonight. Let's open up for a few more questions.
So the only bits out of the chat, Greg's made a couple of comments of
Yeah, I could throw a couple in there, Ron. One that I did find really odd working with it was, yeah, that concept of being in a role and going use role, and also just even the DDL. I always think of a role as something you add members to, and the way they did it was sort of like you grant, I presume it still is, you grant a role to a person.
Correct.
Yeah,
Correct.
which
You can
sort of
grant roles to
felt
roles.
odd. Yes.
Yeah, it's dissonant when you're coming, like Oracle people are used to it, but when you're coming from the SQL Server world, as I was, it's one of the things I think SQL Server does better. The other one that Greg and I were chatting about before the call didn't actually come up during the demo. I thought I had something in there that would show it, but it didn't, is case sensitivity. When you use...
Yeah, that's actually normally a showstopper for me, although there's parts of Fabric that are case sensitive too, and it just drives me balmy. Yeah, so.
Yeah, we can work around it. We can set up a case-insensitive database, but where you feel this, folks, is that column names are case-sensitive. And if you're used to working in a case-insensitive environment, you can type something in lowercase. The system will dynamically convert it to uppercase. So your code might say lowercase column 1, but if you then need to refer to that in a quoted string, you need to refer to it as uppercase column 1, and you need to remember
that drove me absolutely crazy. It's not even just case insensitive; it modifies the case of what you type across into sort of what they call it, screaming snake case, with the all capitals and underscores between. Yeah, but anyway. Yeah, that was a bit. I found that odd.
We do have ways of improving that. It's still a dissonance for people who come from SQL Server. If you're coming from Oracle or DB2, you don't notice it.
Yeah, it felt very 1980s, that sort of thing, or 1960s. But you could work with columns and things, but you had to stick them all in double quotes if you wanted to get it to stay the way it was. Just a couple of other things that came up in amongst the things you were talking about. Fabric also did away with the concept of distribution, like replicated hash, that sort of stuff's gone. You can, in Synapse, you can go out and get a list of files using OpenRowset. You can get file names and paths and that stuff. And there's now options in Azure SQL and stuff for doing that as well. It's something that was driving me crazy for years that you couldn't do it. Like I could load files, but I couldn't get a list of files. It was just a silly thing. Yeah.
What I like about the way we do it is the way that you can use the results of that query and dynamically interrogate it and so on. So those sorts of things I find really helpful. Any other questions? Yes.
Yeah, I have a question about first data sheet. In data sheet, Snowflake says that there is not in data moon.
Sorry, I'm not catching the first word you said.
Okay. In data sheet, Snowflake.
Data share, yes.
Data sharing. Snowflake says that there is not any data movement.
Yep.
But what happens when we want to integrate between a Snowflake partner and non-Snowflake customer? For example, we can think about a company like Netflix.
Yep. Okay.
And they want to share data with non-Snowflake customers. For example, they have a content partner which have a other dedicated SQL.
Yes.
So what is the best thing for sharing data? For example, they have some crime content and they want to share the statistics and maybe the other partners, and they want to use the data in their data warehouse environment. So what happens
Yeah.
Indeed.
Okay. Basically, Snowflake sharing has two flavors associated with it. There is a Snowflake share, which is where your Snowflake and my Snowflake are able to query tables that I've shared with each other. So that's one. But the case that you said is where I have Snowflake, but you have SQL Server. In that case, we create what we call a reader account, which says that you don't need Snowflake. You can just use a client tool and access the tables that are being shared by that customer. One thing you could do, for example, is create a linked server from managed instance that would connect to Snowflake using a reader account and capture the data that way. But that would be yes, it would. Even though it wouldn't necessarily be a copy in the syntax of the query, at execution time, it would pull all the data across the wire in order to execute that query in managed instance. So you would have data movement at that point. However, if you were only using Power BI, for example, to access the data that I had shared, then you would be using it just as if it was a connection to my database, and there'd be only the data movement to Power BI at that point.
You mentioned earlier the preview and upcoming releases on how much of the functionality is going to continue over, keep every caveat and usage of
Yeah. Is this where we get
consistency out of that?
Yeah, no, this is all part of that. It's designed to be an OLTP solution, and it's where the limits are in the first instance are in the number of transactions a second. We're expecting somewhere around 10,000 transactions a second. The dream is 100,000. That's where we want to get to, so that it puts it into the realms where we say that it's feasible to use for any LOB system. But the numbers that we're talking about at the moment, I think are suitable for the departmental systems rather than for the mainstream systems of an organisation. But of course, that depends on the type of organisation. When I talk about organisation, I work with companies like Coles, National Australia Bank, etc. So I tend to think in their sizes, and not every customer's at that size. If you were a smaller business, then you would probably be able to act satisfactorily on Snowflake. However, there's one more caveat. The line of business software to run on top of that won't be on Snowflake for some time. So if you're writing your own software, yep, go ahead, knock yourself out. But it'll be a while before we get the Salesforce or the SAP or whatever running on Snowflake. Yes, correct.
Is there a reason, I mean, just writing that word of interesting. Is there a reason I would use Snowflake OLTP versus Salesforce?
Yeah, that's a really good question. There are two parts to the answer. One part is the Snowflake marketing thing, and that's where we would like you to have one data platform that runs all of your data in much the same way that Microsoft would. Microsoft would say SQL Server is the answer for everything. You know, the answer is always SQL Server. You can run everything on that. The second part of it is that from a technology perspective, the ability to query and analyze your transaction data without having to do any extract or transformation associated with it is where the value of that's going to come from. So if you don't need to use, say, an ETL tool to take the data from the OLTP system to the OLAP system, then you're going to get substantially better analytics out of it. Then you could take Kafka out of the equation, for example, because you already have the data sitting there, and it will have all of the Snowflake features like streams and tasks and all those dynamic SQL things that you saw me doing and so on, available as technical features to you to use for integration.
I had a couple of questions around OLTP as well. Is the micro petition going to be structured differently, or does it have the same format?
No, it's a different structure. The that supports the OLTP part of the data. And in fact, the table will be represented in a dual sense. It will have some that is represented in micro partitions and some that is represented in something closer to a row store. And that's because the micro partition
uses compression.
Well, not only that, but if I've got a 50 megabyte micro partition and I want to update one row, I have to rewrite the whole 50 megabytes as it stands at the moment. And that's a performance issue. With OLTP, you can't afford that. So that's why we need that row store capability that'll be backed by the other store in order to handle that rapid single row update.
You guys have written a whole new engine.
It's a new part of the engine, correct?
Yeah. But you've added engine components to facilitate row store.
Correct.
Yeah.
Yep.
And does it support time travel?
Yes.
I heard an overback.
Actually, XSQL.
Yeah, exactly. The guy that's working.
Yeah, XSQL, and the CIO was, the CEO was ex Microsoft IT.
Correct.
I recall reporting back in the day.
Yeah.
But yeah.
You'd see a lot of familiar faces.
It's not new stuff that they're building. They know what they're doing, I think.
Yeah.
That mean you can just do straightforward joins between your OLTP and your OLAP
Yes.
tables.
Yes.
Okay.
Will OLTP, sorry, will you?
Yeah, no, that was all I was
Will
asking.
OLTP support foreign keys?
That's a subject that's an ongoing discussion.
Objective is yes, but whether or not that's delivered at day zero is something that I'm not sure.
Okay.
So back to your bread and butter scenario, so to speak, as things stand, analytics. So you load the data in, you ingested the data, then there's stored features after that, you can apply the business rules?
Yes, we support stored procedures in SQL, JavaScript, Python, so you can have your choice of language on what you use for stored procedures.
Generally, they moved away from. You guys looking to maintain that?
Yes. Yep. The other feature that I didn't demonstrate tonight that's worth calling out is something that we call Snowpark. Now, again, something that kind of, sorry. Something that kind of irritates me about Snowflake is that everything is called snow something. It gets really tiresome to remember which snow word it is. We've got one called Snowpark, and if you look at that sideways, you see that that's Spark with snow in the middle, right? This is our alternative approach to Spark. Now, if you're running Spark clusters, be that Apache Spark or any of the other competing Sparks that are out there, and you've got your data in Snowflake, the slowest operation you can do is take the data out, do something in Spark, and then put the data back. The way that Snowpark works is it's a library that replaces the data frame. And once you've got all of your data frame operations in your code, at the point where you do your lazy evaluation in Spark to decide what code gets executed to go to the database, we rewrite that code in SQL. So we convert all of the data frame operations into SQL and push them down to the database. So there's no heavy data movement. It's only the result set that goes back. This means that if you're doing data engineering work in Spark, we can make very substantial performance and cost savings over needing to move that data in and out of a Snowflake environment.
So how does that fit with maintaining separation of storage and compute? See that?
Yeah. Well, you're only needing one Python instance, which could be a Python Azure function, for example, to execute the code. You don't need a separate PySpark cluster in order to run that. Secondly, when we push the SQL down, then that's just executing on a warehouse, on a compute engine, and the data is still separate to that.
So would you say your primary language of data manipulation is SQL?
Yes, Snowflake's DNA is SQL at its heart. After that, I would say our primary intent, this is my opinion, right? This is not an official Snowflake statement because I don't recall an official statement on this. We try and do everything else based on Python, but also offer Java, Scala, etc. associated with that. Now, there are a couple of things that are Java first. And we have a streaming API, for example, which is Java first. The Python version of that's not out yet. But in general, if you're a Python or a SQL developer, you'll feel exceptionally comfortable within Snowflake.
And in SQL, you get a lot of options. If you look at the execution plan, obviously indexing that you can play on. If my Snowflake query is running slow, apart from increasing the cluster size, what other options now?
Yeah, you've got a lot. I'm just seeing if I can get to it to show the screens off. Let's see if I can show it.
I'm sorry, this is my first Snowflake presentation, so I'm not excited.
That's all right.
Mindset.
I just clicked on something called View Query Profile. Now, unfortunately, this is a little query. It didn't have any complexity in it, but here you're seeing the query plan that was run. And it's saying that that's a horrible query because it only needed to show one micro partition in order to satisfy that. Normally what I'd see here is in a complex query, I'd see a very big query tree sitting here. There'd be a table here which told me which were the most expensive nodes in that query. And that right-hand panel here where it's got statistics would have a lot of information about what was happening on each of those nodes at that time. Really, the number one thing you can do to tune a Snowflake query is to look at these two rows here, which is total partitions and partitions scanned. That's where I talked about rejecting and pruning micro partitions before. You get that partition scanned number as low as you possibly can, and that improves your query performance out of sight. But you will see in different queries, you'll see a bunch of recommendations that come up about things that you can do. We support things like materialized views, etc., which can be used to accelerate queries. Search optimization service I spoke about, which is an inverted Bloom filter to accelerate finding single rows in large sets of data. Something we call query acceleration service, which is if we're running a query that the optimizer looks at and says that's going to need a lot more resources than you currently have available in your cluster, rather than taking a long time to run it, if you're okay with it, I'm going to grab some extra serverless resources and apply them to that query to make it run faster. So you can set up a parameter that says you will allow it to acquire extra resources at per second cost in order to add some horsepower to an abnormal query. Okay, time for one more question. Someone has? No? Okay, thank you, everybody. Been good to have a conversation tonight. Good to be back in SQL world. So thanks, everybody, for coming along tonight.
Thanks, Ron. Good.
Thanks, Ron.